Thank you very much. So we would like to start TE-03, NoSQL database strategy. The instructor is David Pearson, Business Development Manager, Amazon Web Services.
David Pearson.
Thank you. It's great to see a great turnout here for such an important event for us. So thank you for coming. I'm going to focus in this session on NoSQL, how we think about NoSQL, why we built things that we do in NoSQL from a product perspective, and also talk through a little bit about how people are using NoSQL and how you can use NoSQL. So let's start. It's important to understand where NoSQL came from. NoSQL was driven by the scalability limits of high-scale workloads on relational databases. Amazon wrote the NoSQL white paper that generated the NoSQL industry. It's called the Dynamo White Paper. That was in 2007. But years before that, Amazon was experiencing what many of our customers today experience, and that is the relational database, when faced with a simple, high-scale workload, is unable to or too expensive to manage that workload. And so NoSQL technology was created initially as a technology, and what we would consider today as self-managed database. And this is what we consider as the distributed era. What we discovered within Amazon was this technology was wonderful when it was implemented, but it was also very difficult to move with applications. It was difficult to start and to grow and to scale quickly because developers had to be experts in distributed systems in order to make the database operate optimally. And so the request was very strong for an effortless version of NoSQL. And interpreting this, we moved ahead with what we consider the third generation or the next generation of NoSQL, and that is to bring it into the cloud as a managed service. And so this is what we're going to talk about today. So as a quick guide to how we think about databases, first it's important to let you know what are these services that we're talking about. So databases is one of the three core services within AWS: compute, storage, and database. Databases are different in that they are very high effort, high maintenance. And so when we deliver services like you see there, Elasticache, DynamoDB, Redshift for data warehousing, and RDS for relational databases, we automate them and make them a managed service. And that is to ensure that the effort required to maintain and manage a database is our effort, not your effort. When we talk about strategy, it's very important we talk about cycles. In this case, self-reinforcing cycles. You may have seen this previously. This is the pricing philosophy that we have at AWS, and that is based on customer usage. Customer usage drives more infrastructure for us. We deploy the infrastructure that you use, and as we deploy more infrastructure, we can buy it cheaper because we're buying an enormous amount. Economies of scale. That allows us to lower the cost of infrastructure and pass those savings on to the customers. And of course, that is interesting to customers, and so we get more customers. And so this cycle is self-reinforcing, and it spins faster and faster as we execute on it, if we execute well. We also have a cycle that we use within the service teams, and this is the service philosophy, how we engage and talk with and understand the problems and challenges our customers face, and take that information and turn that into requirements and priorities and features and services. New services that you've seen launched in the last couple of weeks are results of this type of approach. In the database world, we've seen Redis delivered because customers wanted it. We've seen RDS Postgres delivered because customers requested it. We have features within all of our services being worked on now and have been delivered previously because customers have requested it. And so the same sort of philosophy, a cycle that self-reinforces and spins faster, gives value both to the customers as well as it does to us. We also think about, in database terms, is the challenges, the requirements that never change. It doesn't matter what database you have. Constant challenges are those that we use to form a baseline when we're thinking about new services and thinking about features. Performance is very important. No one ever asks for a slower database. No one ever asks for a database that's less reliable, less trustworthy. No one wants to pay more for the database that they have, and no one wants to spend more time managing it. And so these are the principles, if you like, that we use to build a baseline on which we build our services. So when we look at traditional database architectures and how they've been implemented historically, on-premise gives you the ability to have to worry about the infrastructure. And so when you're deploying a database, you have to think about the server it's on and how you can build and configure that server to make the database work quickly. And so what happens is that the best database for the applications often becomes the one that is the most manageable, because managing 3 or 4 databases for one application is impossible. It's too much effort. And so we consolidate all of our workloads, whether they're high-scale queries or searches or logging queries, hot reads, complex queries and transactions. We do them all in a single database that offers us the most versatility. And this is the role the relational database has serviced over many, many years. It's a beautifully versatile database engine. It services all these workloads well, but as we saw in the evolution, when you add scale, your options reduce significantly. And in the case of extreme scale and often cost, a relational database becomes something that's very difficult to justify. And so instead of focusing on the database that's the most manageable, when we take a cloud perspective, we think about workload specialization. What the cloud enables you to do, especially with managed services in the cloud, is to reduce or eliminate the administrative effort associated with managing a database, relational or otherwise. And so this is how we think about databases. We think about it more as a data tier, where the right sort of workload is serviced by the right sort of database. So the best database now becomes the one that services the workload in the most efficient way. And when we put some names, you may be familiar with some of the names to these services, you can see this is how we build our database strategy, our data strategy. Our database strategy are those blue icons where we're talking really about structured application data, but data is bigger than just the structured data stores. And so our data tier approach that we have in the cloud highlights the fact that you have all these choices available to you and enabling you to use the right data store, the right element of the data tier that will optimally service your access patterns. Database options enable choice, and choice is extremely important. Not just the type of workload, to say you can have cache, NoSQL, you can have a relational database or a warehouse, and we'll provide all of that. We do that. But within these categories, again, customers ask. They don't want just MySQL, we also want Oracle. We don't want just MySQL and Oracle, we also want SQL Server. And we also want Postgres. So as customers give us this feedback because of that cycle that I described, we understand the challenges, the importance, the priorities of those challenges, and we respond. And this is how new services are created. And so with RDBMS, using the Amazon RDS service, relational database service, we now have these 4 platforms offered as choices. In caching, we have Amazon Elasticache, and you have the choice of Memcached, you have the choice of Redis. Again, Redis came because Memcached was great, but people love using Redis. So that's what we did. When we look at DynamoDB and Redshift, these are technologies that are 100% Amazon. They're completely our technologies. And so we're not managing another engine. Now, this is a good thing in that it enables us to build completely cloud-ready from the ground up a service that's dedicated to its function. But we still can provide choice. So, for example, in DynamoDB, we offer key value access patterns as well as rich query access patterns. And there's a subtle difference between them, but they are important differences. In Redshift, you can have a schema you can just bring in from a relational database, a typical ER diagram that describes your entity relationships, or you could have denormalize that entirely, or maybe normalize that into a star schema or a snowflake schema. All of these schemas will operate very efficiently in Redshift because Redshift was designed to enable these choices to be made so customers don't have to change. They simply have to bring it in and work with it. And so choice is very important. Today what I'm going to focus on is the NoSQL. And caching is not in the history of NoSQL, it preceded NoSQL, but because it's a key value relationship, it's since merged in and we manage it as a NoSQL data store. So, Elasticache and DynamoDB, they are both very fast and they're both fully managed. Elasticache is an in-memory caching service. And caching is, as you think, leverages the power of memory to give you super performance. The core benefit of Elasticache is that it's very easy to use and manage, very simple to deploy, operate, and scale. DynamoDB is more of a traditional database we think of, where we're using it in an application sense. But as a NoSQL database option, it has to be fast, it has to be durable, it has to be a number of things, which I'll talk about. Most important thing, I think, to remember about DynamoDB, it delivers committed performance, committed reliability. Those things that don't change. Let's see how caching is deployed. This is a very typical architecture where a cache is used. We probably see this 90% of the time, probably more than that. A cache is used to reduce the pressure, to reduce the load on a relational database. And this is a very good architecture. The relational database may be holding your customer data, and when a customer logs in, concurrent user, then you could cache that user's data in something like a Memcached or Redis, and that means when the customer comes and visits their data, they get a microsecond latency experience instead of tens of milliseconds. So it's not only a better experience, but it's taking the load off the relational database, so you don't have to have a very, very big database in order to service your workload. So this is very popular in online gaming, for example, which has very high concurrent users. And of course, because it's in memory, memory reads are much faster than disk reads, and so the read performance is much higher. So this is what we think of as application acceleration, and it's the core focus of how a caching solution is optimally deployed. Memcached and Redis are different protocols supported by Elasticache. And what's important about Elasticache is that it supports those protocols absolutely. And so this enables you to pick up a Memcached application that perhaps you're running in-house, and then simply point it to a new cluster that you've launched in AWS. And so it's completely compatible. No code changes, nothing required. On top of that, we like to extend these products a little bit more. So as well as the benefit of multi-node clusters in Memcached, we've introduced features like auto-discovery, and that enables you, through a client library, to basically add nodes to a cluster to make it bigger and have those nodes be recognized automatically by the clients and therefore used. So you don't have to force that relationship manually each time you increase or decrease the number of nodes in your cluster. So it's very important. It takes away a lot of pressure from the administrator at just the time when you don't need to be doing things like that. Because if you're scaling up, obviously there's something going on, and it's important that the experience of the user is seamless. Memcached is non-persistent. It's a pure cache. It's in memory, and it's great at what it does. Redis, a big part of why that was requested was because it does have a persistence option. It's not what we would consider a super durable data store, because its persistence option is it's more backup, write-ahead log style, which doesn't give it as high durability at scale, but it's still very good at low to moderate scale. Redis we enable you to offer read replicas in Redis, and a lot of people deploy them in different availability zones within a region. You can also back up and restore your cluster, your Redis nodes. And so these are features and capabilities that were built. Some of them were built at launch, but many of them were implemented as a result of customers requesting it after we launched the minimal product and say we would love this to be supported. So then we build that as well. So part of that customer feedback loop got us to where we are with these services. With DynamoDB, I mentioned it and Redshift are 100% Amazon technology. It was designed for the cloud, it was designed in the cloud, and it was designed by the people who originally wrote the white paper that created the entire industry, the transactional NoSQL industry. And so as well as the constant challenges that our customers face, we had the ability to look at the technology and the challenges with existing technologies and then leverage the cloud to make those go away and make things better. So this was a unique experience that we were faced with, which we fully embraced. So a lot of what was focused when we optimized for the cloud is to reduce the limits, overcome the limits of managing it yourself NoSQL. And NoSQL is a wonderful technology, but like any technology that's complex that needs to be managed, that complexity can create challenges. The challenges can be to do with the effort required to scale, rebalancing nodes, resharding clusters, and so on. It can be a difficult amount of work. And so when we released DynamoDB, a big part of its focus was to ensure that the effort required to do these difficult things was very close to zero. So the core tenets, the basics, the fundamental principles that we built DynamoDB upon were these. It had to be fast. And I'll tell you what fast is, because it's not just, let's be fast. That's too simple a solution. It's too simple to say it needs to be fast. When we say fast, it has to be consistently fast all the time at any scale. Otherwise, it's not acceptable. It has to be scalable. Scalability is the original use case for NoSQL. And of course, you can't build a NoSQL service without having it to be massively scalable. So a pure distributed system will have no limits to its scalability. And that was obviously important for DynamoDB. It has to be reliable, which really means that it has to be available all the time. It has to be durable all the time. It's not acceptable for data to be non-durable in the interests of greater performance. To reduce the durability of your data to get some more milliseconds of speed is not a decision that we enjoy, and so we don't enable that. You get both. You get very low latency and you get absolute durability all the time. It had to be administrative free. It had to be very low effort, zero effort if possible, to provision, to scale, to operate the database. And of course, it has to be low cost. You've seen our cost cycle, and we're in that cycle. We've dropped prices. We reduced storage costs by 75%. We reduced the throughput costs. We introduced reserve capacity, which enables you to deploy capacity at about 1/4 the price of the on-demand rate. And so there's some serious options there for optimizing for cost that we released. So when we talk about performance and the importance of consistent performance, it's really important to understand two things here. One is that we have a very high variation on the workload, and the second thing is how flat the latency curve is. They're obviously on different axes here. So I've introduced both the average latency, which is a good guide to the average experience of the user, but it's not a good guide to the volatility of that latency. And so to take volatility out, we monitor at different levels of granularity. In this case, I've reported TP90. So TP90 is the worst experience of 90% of the workload. And as you can see, that is a little bit higher, of course, by about a millisecond, but it's also very flat. Internally, we monitor all the way up to TP 99.9 because the consistency of performance is very important to us. This is a slide that James Hamilton, if you haven't seen his talk from reInvent, it's on YouTube, I recommend it. It was all about scalability and why it matters. From a DynamoDB perspective, this is obviously an old slide from October, but you can see how the adoption of DynamoDB has been. The massive amount of scalability that we're servicing through tens of thousands of workloads in the cloud. So this is requests served per month in a single region, and it's already in the trillions. DynamoDB is provably durable. Provably. What that means is data cannot be, is never in a state where it could be lost. When a write is accepted by DynamoDB and the application has been told that that write has been acknowledged, what it means is that data is being replicated and persisted. It exists in at least 2 of 3 locations. We replicate to 3 availability zones constantly. And it's been persisted to the custom SSD stack that DynamoDB is built on. So writes are extremely durable, even with that low latency. With reads, a lot of people assume that you can't have eventually consistent reads in a you can't have consistent reads, in a distributed system. You can. So DynamoDB gives you strongly or eventually consistent reads. It's an option. This design also allows us to deliver extreme availability, very, very high availability. DynamoDB was basically designed for what we call Tier 1 applications. These are applications that require 99.999, 5 nines of availability or better. And we have customers who are realizing these benefits today. So when we talk about NoSQL, and you understand a little bit about what we built and why we built it, what's really important is to understand also how people are deploying it. So here's a sample of some of the use cases that are being used to drive, with NoSQL databases, to drive the business of many of our customers. So you probably recognize some of these there. Let me look at 4 of these. So I'm going to walk through gaming, ad tech, connected devices, and one I call state management, and I'll explain what that is. So with online gaming, the best thing about online gaming is they give you great screenshots. You always get some very impressive artwork there to show. So we show it. This is a screenshot from Fruit Ninja. You may be familiar with that game. They moved from a relational database to DynamoDB because they were under pressure, a very normal situation for gaming companies. When their game gets popular, the scalability matters. And so they moved, and they went from 1 million to 8 million users in a 2-week period. And that's a very typical story. One of our customers here in Japan went through a similar experience, Riplation. Their popular game, The Knight and the Dragon, runs entirely on AWS using DynamoDB. And the reason, of course, was because they wanted the effort for their creative developers not to be focused on infrastructure. They wanted that effort to be focused on applications, a better game, a faster game, a more interesting game. And so they chose DynamoDB as a managed service. So here is the architecture. Many gaming companies use multiple data stores. We often see RDS and Elasticache and DynamoDB together, but it depends on the type of game and the type of access patterns. In this case, Replation managed with a single data store, DynamoDB, and then they experienced what many companies experience, and that is growth, sudden growth. Their active users, their daily active users, surged from 5,000 to 30,000 in less than a week. And this would normally put tremendous pressure on the infrastructure. But because they'd architected it with Elastic Beanstalk, they were enabled to scale essentially their stateless infrastructure very quickly. A few parameters, double, triple, 10 times the scale. DynamoDB is a case of increasing the throughput. A very important concept in DynamoDB is provisioned throughput. You ask for throughput, and that's what you get. The service does all the sharding, the allocation of resources, the distribution of data in the background. You ask for 1,000 writes a second, you get it. You ask for 10,000, no problem. 100,000 or 1,000,000, just ask. And so this is what Replation discovered, was they just had to turn up their request rate to handle this surge, and their service was perfect. We see many gaming patterns on NoSQL. NoSQL is very suited to gaming, to online gaming. Small, micro gaming patterns or larger ones. We generally see a lot of write-heavy workloads find their way to something like DynamoDB, where durability is very important. And so game data, instrumentation from games, achievements, session information, purchasing, things like that are very popular in DynamoDB. On the caching side, because it is a cache and you don't want to depend necessarily on the durability of that data, transient data is very popular in Elasticache. Leaderboards, database records, loading from a relational database into the cache to offload that pressure from the database and give a better read experience. Hot counters, very popular in Elasticache. We're going to talk about digital advertising now. This is another industry that has very, very low tolerance for latency, especially with real-time bidding platforms. So you can see some common patterns there, from simple ad serving all the way to the complexity of a real-time bidding platform. All of these patterns are adopted by our customers. And you can see some of their names there. What's important in a real-time bidding platform is you've got 100 milliseconds to service the request. If you take 101 milliseconds, you've spent some cost, some effort, some energy to get the request there, and it's thrown away. So it's better to serve nothing than to serve at 101 milliseconds or greater. And so that's a very important boundary that we have. And consistency at any scale is a very important attribute to have for any data store. And this is what AdRoll found. AdRoll is one of the largest retargeting providers in the world. They operate in over 100 countries. They work with a real-time bidding platform, and they do retargeting. So retargeting is the process of when you visit a site, maybe you've looked at something, a pair of shoes online or something, and then you move on to something else. When you visit another site that's one of their customers, the ad that will be shown is the pair of shoes you were looking at. This is called retargeting, and it's designed really to remind people that perhaps they wanted to buy those items. So it has a very high conversion rate, very high value rate in terms of advertising because it's very, very targeted. So AdRoll's infrastructure, for a small team, they run a massive organization. 4 regions, they replicate continuously live to 4 regions. over 120 billion, with a B, key fetches every day. And this is the real-time bidding platform, constantly interacting with their infrastructure. Now, if you think of what does 120 billion look like, that's over 1 million operations every second. So these guys run fast. Most importantly, look at the bottom statistic. A less than 3 millisecond uniform latency across all of their queries. Under 3 milliseconds, flat. And less than 10 millisecond for 99.95% of all queries. It's a TP 99.95. It's very, very consistent. That all runs on DynamoDB. It's enabled them to grow their business very quickly. They're growing at something like 15,000%. They're one of the fastest growing companies in the US. And obviously, they rely heavily on managed services so their teams can focus on their application. If we look at the basics, and one more thing about AdRoll is they're very happy. One thing they do very well, and this is a best practice, is they do what we call design for scale. Design for scale with a database is always recommended at any scale. Why would I say that? Designing for scale with infrastructure often means you deploy more infrastructure than you need to enable you to scale into that infrastructure, but not in the database. Designing for scale in the database means you design your schema to be super efficient. Now, what a super efficient schema will give you is a low-cost schema. And so even if you don't scale very high, you'll be paying very, very low costs for your throughput. If you do scale high, then your schema is ready. You don't have to do any re-engineering. You don't have to do any migration. With something like DynamoDB, you just turn it up. And that's what AdRoll have done. They've gone from tens of thousands requests a second into the hundreds of thousands of requests a second by just asking for more throughput. So they're very happy to the point where they pay more on snacks for their developers than they do for DynamoDB. And the developers are not huge. They're very focused. If we talk about a reference architecture for ad serving, this is a case where the ad request comes in and the impression, if you like, gets sent back. And then the impression gets served from S3 via CloudFront. And the click-through, if that is done by the customer, gets tracked. So this is the full experience for an ad-serving architecture. I want to focus on the data tier, specifically around this relationship between the analytics layer and the real-time layer, because it's a very important cycle that's created between these two entities. And we see a lot more, since we launched Redshift, we see a lot more use cases adopting this sort of approach that were previously done with like a Hadoop solution, which would simulate SQL, but it's much more efficient in Redshift. So here are some basic tables here, where sessions are logged, and then they flow into Redshift, and your full history is maintained in Redshift. The history is curated into a profile, and so periodically the profile is updated, and when the real-time pattern comes through, the ad gets served very quickly. It's a very simple architecture. It's a personalization architecture that is used in retail, where instead of serving ads, catalog items are being served from browsing history and purchase history. So it's a generic pattern that is very popular across a number of industries. Connected devices is another area that has been adopted aggressively in NoSQL. The thing about connected devices are these sort of curves are very normal. Dropcam is an example of video service who found this. They called it suddenly petabytes. They were ingesting enormous amounts of data. This is the architecture they used. The core attributes here are that the data was flowing into S3, the metadata into DynamoDB, and then the servicing back to the customers was done through CloudFront. DynamoDB reduced their delivery time for events from 5 to 10 seconds down to 50 milliseconds. That's the other advantage you get moving to NoSQL. In a logging situation for a connected device use case, hypergrowth is normal. So while we think we write a game and the game goes viral and we see a lot of users, in a connected device scenario, the potential for that curve is even steeper. If you think about customers and devices, and as data architects, we think about the number of data items per device, the size of each item, and then the frequency of collection. And we may tweak these. We may increase the granularity of the data that we capture because it gives us more useful information. We may collect it more often. And this has a compounding effect on the amount of data we have to manage. And so gigabytes per hour quickly become gigabytes per second. And this is why a very popular architecture, very simple, it's oversimplified in this case, but a very popular architecture involves Kinesis as a log capture hub, where logs are ingested directly into Kinesis at very high scale. Kinesis will hold those logs for 24 hours in a stream that can be subscribed to by other services. So instead of having data flow from one tier to another, it's now available to all tiers in near real time. And so real-time patterns are serviced through DynamoDB, pulling the data out of Kinesis, putting them on a dashboard in near real time. The same data at the same time flowing into Redshift, and so the access patterns there, the analytical patterns, are used to produce reports and analyses and trends. And meanwhile, because Kinesis is only durable for 24 hours, the data, if it needs to be retained, flows into S3 as a durable archive, and maybe into Glacier beyond that. State management is the last of these use cases that I want to describe. And this is the internal use case. It's used very heavily at Amazon. It's used very heavily at AWS, where many services rely on DynamoDB as a fast, durable backplane. And this is how different companies, I've listed some there, also use it for their internal applications when they build their own fabric or backplane. So News International is a good example. They implement their paywall using this sort of design where the user will navigate to a web page on their news site, and then very quickly in the background, there'll be a question asked. Are they allowed to see this page, yes or no? And it'll come back. So that is not a core transaction to the business of serving the page and the user experience. It's a supplemental transaction, so it has to be extremely fast, and the data has to be durable. You can't lose that data. And so News International, they had assessed 5 different NoSQL technologies, and DynamoDB was about to launch, and it was perfect. So they adopted it, one of the first adopters of the technology, and it's been perfect for them ever since. And it's a very typical example of how people are using a durable, fast, very consistent data store to drive their backplane. So I'm just going to close now with 3 final thoughts. The first is that specialization is very good, very good. In the database world, we haven't been able to do this because the effort required to manage infrastructure was so great. Databases are high maintenance objects. In the cloud, that goes away, especially managed services. So specialization now becomes a function of choosing the right database for the workload. And if the best architecture means we have 1 or 2 or 3 types of database for the application, that's okay too, because they're still easy to manage. Optimize is super critical. If we design for scale from the beginning, regardless of the scale, the eventual scale of the application, then you're minimizing your costs from the beginning. And so this is critical for NoSQL because the potential for NoSQL to scale is much greater than it is for other applications. So even if you don't think it'll scale and somehow it does, you want to be ready for that. Both technically able to scale and two, paying the lowest price for that throughput. The third thought is really automation, and it's about managed services. Focusing on what makes your company better, what makes your game or your application faster, more useful to your customers, is what we want to enable. Taking away the focus on infrastructure and hardware and patching and upgrading is not something you should be doing. And so leveraging managed services reduces what we call undifferentiated effort. The effort you spend that doesn't make your application better, faster. It doesn't make your business grow better. It's a distraction. And so managed services take that distraction away from you through the power of automation. So with that, I'd like to thank you for joining. I will be sticking around for about an hour after this. I appreciate your attendance.